All right, welcome back. So today we'll be talking about induction. So this is a very important concept. I would say without induction, you guys will not have your smartphones or computers or even electricity. So let's jump in here. Um, these days you'll see often if you travel, you'll often see wind turbines. So they are used to generate clean energy out of the wind. So it's basically there's a coil inside it, and then the wind drives the turbine. So there'll be motion of the turbine here, and that generate electricity. Okay, so um, let's move on here. So basically, the way that you can generate electricity is based on Faraday's experiment. Okay, so in which that there are two types of Faraday's experiments you can do. One type is having like a coil in the primary circuit, which is connected to a resistor and a power source, and there's a iron bar over here that goes through this coil, as well as there's a second coil here, which we call a secondary circuit, which is directly connected to a galvanometer that measures small current in the circuit. So what happens is when you close the switch, now you have current going through this coil, it will generate a magnetic field, and magnetic field is going to be restrained inside this iron bar over here, and so it'll present magnetic field of this location of your secondary coil. And if there's a change in current, then there's change in magnetic field. So then you'll see actually a current will be sensed in this galvanometer. If you open the switch later on, then you'll see the current will go in the opposite direction. You'll see the needle switch to the other direction. Now, just shortly after you close the switch, you'll see a spike in the current, but the current will then go back to zero. So that means when the current is stabilized in the primary coil circuit, then you'll have you actually don't have any electricity generated in that case. Okay, so once current is stable, you lose the generated electricity in the secondary coil. Okay, so basically, through this type of setup, you can observe current generating in the secondary coil. So the current in the secondary coil will be zero if the current in the primary circuit is not changing, and the current will in the secondary coil, there will be current in the secondary coil if you have a current changing in the primary circuit, either if you just close the switch or open the switch. Okay, so if you just close the switch, the current is increasing. If you just open the switch, the current is decreasing in that sense. Okay, and the magnitude of the induced current in the secondary coil is proportional to the rate which the current is changing in the primary, or we can say at which the magnetic field is changing at the primary coil, because we know by this point that if you have current, then if you have a magnetic field in the generator due to the current. Okay. Another type of Faraday's experiment will be a simpler one that you can use a bar magnetic here, and then you can form a simple coil like this. You just use a wire, form a couple loops there, and if you are approaching the bar magnetic to the coil, then you'll see there's a spike in the current there. Now, if you stop moving the bar magnet, it will go back to zero. And then if you're moving the bar magnet away from the coil, the current will be spiking into the other direction. Okay. And then also the other way around, if you flip it, okay, now this is the other way around. In that case, because you flip the poles of the bar magnet, okay? When it's stationary, you do not have any current, okay? So this is similar, pretty much similar. So the current induced in this coil or this circuit is basically due to the magnetic field changing, okay? So this would be the same scenario as the previous case as well. All right, so how the current is changing with respect to the the magnetic field. So we introduce a quantity called magnetic flux. So in this case, to enable us to calculate the induced current. So first we'll calculate what's the amount of the EMF. So EMF refers to the potential induced. Okay, so in that case, we are calculating the potential first, and then if we know the resistance, we can use Ohm's law to calculate the current. So the magnetic flux is definition. This will be somewhat similar to the definition of electric flux. So it's a measure of how much magnetic field through a area of A. So flux magnetic field is the magnetic field cosine of theta times A, which you can do magnetic field times the area of the surface and then cosine of theta. So the theta angle is measured between the normal direction and the direction of the magnetic field. Okay, so that's a cosine factor there. So you can see if field is perpendicular to the surface, then you get maximum flux. If field is parallel to the surface, you get minimal or zero flux there. The SI unit for magnetic flux is Tesla times meter square. Okay, so Tesla comes from magnetic field and meter square comes from area. Or it has its own name called Weber. It's WB, capital W, small b for the abbreviation. Okay, let's take a look on this first example here. So this one says a magnetic field is oriented at an angle of 67 degrees to the normal of the rectangular area. Okay, so you can maybe just visualize this guy. So magnetic field is this guy here, and then it's 67 degree to the normal. So normal direction will be in this direction here. The B field is going in this direction, okay, which is like that, B field. And the angle here is the theta, okay. All right, so this is the same angle as the defined in the equation BA cosine theta, okay. So this is the theta, and it's asking you what's the strength of magnetic field. So it tells you the flux, okay. So the flux is that, and then it tells you the area. It gives you the angle, okay. So basically, according to this flux equation, flux equals to BA cosine theta. So we have just everything else, but the magnetic field that we are looking for. So we can rearrange the equation here. B will be then equal to the flux that given divided by the area and cosine of theta. Okay, so the area is given by dimensions, and again, pay attention to the units given here. They are given in centimeters, so you want to convert it into meters of SI unit. Okay, so the flux given for point A, 10 to the minus 5, and that's already in SI unit divided by 5.9 times 10 to the negative 2, and then times 7.8, again times 10 to the negative 2. Okay, so that's your area, and then cosine of the 67 degrees. Okay, and that will give you your B field as 0.027 Tesla. Okay, all right. So let's move on. Now, let's see how we can use the flux to calculate the induced potential or EMF here. So according to Faraday's law, the EMF induced is according to the law of induction, which is the mathematical formula over here. So that gives you EMF equals to minus M. M will be the number of turns of coil in the coil. So if we just have 1, then this n is 1. If we have 10 turns here, then this n is 10, okay? And then times the change in flux over time t. So this is the rate of magnetic flux is changing, or the rate of magnetic field is changing, either way. So this flux has that's flux phi is equal to BA cosine theta. So sometimes you don't necessarily have to have flux, the magnetic field changing. You could have like area being changing, or in some cases you might have the angle being changing. Okay, so either of those three changes that gives you change in flux, okay, over t, then you'll have induced EMF. Okay. Changing flux will be final minus initial, and then changing time will be t final minus t initial. Okay, so that's the equation, the main equation that we will be using today to calculate induced EMF. All right, so let's take a look at some applications first. Okay, so this one I found would be really interesting if you guys some of you guys might be playing some instrument, or some of you guys might like to sing like karaoke maybe, or surface in the chapel to sing. But let's take a look on this demo first. Okay, that's which gives the theory of the pickup coil of the guitar pickup, or in the microphone. Okay, so I'm going to switch to another screen here. All right, wait a second. Let me redo this. Sorry about that. Um, all right.
This is a pickup coil from an rock and roll. This is a pickup coil from an electric guitar. And I hope that you can see that there are 1, 2, 3, 4, 5, 6 magnets right here. Let's prove that they're magnets. Yep, stuff sticks to them. And each magnet is designed to magnetize a string of the guitar. So the strings will be like, well, the pickup would be like that if the strings were like this, doom, 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 in front of it, and you go like that, and it would be awesome. Or we could show it like this, and I think that might make the most sense. This coil here has 500 or so turns. Wow, that's a lot of turns. What is this pen thing? Okay, here, let's get a marker here. We're talking about 500 turns or more. And out of this just comes 2 wires. So let's talk about how rock and roll is made. I'm going to zoom in on just one of these magnets. The magnet's like this, and it has a north pole and a south pole. I don't actually know if the north pole is the one that's sticking up, and I frankly don't really care. But there is a coil going around it like this. Lots and lots of turns. Hundreds of turns, and the coil comes out and goes out, and yeah, so it's got 2 leads leading from it. But in front of the magnet lies a string, and from our perspective, the guitar string is sliced and would appear right there. I guess it's going to be a little bit smaller, but I wanted to show you that when the string is nearby the magnet, then the string becomes magnetized, and you can bet that it would prefer to have this side be south and that side be north, assuming it's a ferrous material. So we're going to set it up like this, and then if you hit the string, boom, you hit the string, that string will shake back and forth, which in turn will change the amount of flux going through this coil. Now, does this coil like having its flux change? But the coil is monitoring the change in flux at every instant. So it's getting this derivative of the flux as a function of time, and it's multiplying that by the number of turns that we've got. So this is a big deal, and then putting a minus sign on it to find.
So when you see derivative of certain quantity, it's just a fancier way of saying change delta of it, but in calculus. Okay, so don't worry about the derivatives here.
the induced voltage on the coil. So the coil is spitting out a voltage function that's sometimes big and sometimes small and sometimes big and sometimes small as the string is vibrating up and down. And we're probably going to get a graph that looks kind of like this. V induced as a function of time will be like this, and the frequency, well, this is like a period or something, and 1 over that would probably be the frequency, but the frequency will correspond to and be exactly the frequency of the vibrating guitar string. So the information about how the guitar string is vibrating is carried in the induced voltage. And this is awesome because now you can amplify this and send it around, and then you can then hear the movement of the guitar string without having to have any sound come from the guitar string and be amplified through the body of the guitar and then come to your ears. So it could just be immediately recorded, or it could be amplified and then played back on speakers, etc. So let's make a little schematic diagram of what we've got. We've got a guitar, and I suppose it has to be an electric guitar, and then we can send the signal from the guitar to some pedals, and those pedals can change the sound in a lot of awesome ways. I'm only beginning to explore that. You probably know more than I do about it. And then we'll go to an amplifier. So you're talking about Fender or Marshall or something. And these guys are going to make your sound louder. Not your sound, I should say your signal. So they're going to take a small induced voltage, and even though there are 500 turns or so here, we're going to say that this voltage is rather small, probably in the millivolt range. And they're going to make it in the volt range. They'll make a much, much larger voltage change coming out of that sucker, coming out of the amplifier. Then the amplifier will send the signal to a speaker. If it's not being recorded, it's going to be sent to a speaker. We'll talk about speakers in just a minute. But before we talk about speakers, I want to ask you a couple questions about guitar. For instance, would it work with nylon strings? Electric guitar with nylon strings. Nylon is a kind of plastic. Answer is no. Why not? No. Why not? You figured out. And would it work with copper string? Electric guitar with copper string. What if you, what if you are looking in some fancy magazines and they say that they can get you gold strings, and well, gold doesn't have that much tensile strength, but what if you got suckered into something silly like gold string? Would that work? And you can figure that out. Turns out only a few things will work, and you should discuss that in the comments. But let's talk about the sound you get out of the electric guitar. So if you've got a choice between two strings, and one of them's like this and the other one's like that, assuming that...
All right, I think he has explained enough of the inductions there, so we'll stop there. So to answer his questions, you might think about it will be only the ferromagnetic material that will work, because that part of string should be able to be induced or magnetized, okay, by the magnets there. Okay, so let's go back to the PowerPoint. All right. So we will take a look at this example here, and let's bring up the example in another screen here, which actually will sense my hands in the stylus pens better. So this one says a single conducting loop of wire has a area of 7.2 times 10 to the minus 2 meter square. So this is just one single coil. So that means my N is equal to 1, and it has the area of 7.2 times 10 to the minus 2 meter square, and it has resistance. Okay, so resistance R, which is 110 ohms, and it says perpendicular to the plane of the loop. Okay, so perpendicular to the plane of the loop is a magnetic field of, so B field is given as 0.88 Tesla. Okay, so then so B field is perpendicular to the loop, so that means B field and the loop is actually in the same direction. Okay. All right. So in that case, then the angle theta actually is 0. So but flux equals to BA cosine of theta. So if theta is 0, then this guy is 1. Okay, so it's just then B times A. All right, so it's asking what rate must this field be changing? So the current in the loop is this. So we know that we can calculate epsilon by doing minus m delta phi over delta t. Okay, so this is the voltage. Okay, so this guy is the voltage, right? And then it gives us current I. Now I should be equal to the voltage, right? Divided by the resistance. So it gives us that. So that means we can actually find using this to find this epsilon first, and then we can put epsilon back in here because we know this is 1, so then we can find the rate of changing. So this is the quantity we are looking for. Okay, so the rate that is changing, the flux is changing. So we are actually looking for that thing. All right, so we can calculate epsilon based on this guy here. So epsilon equals to then I times R, which I is given as 0.43 amps, and then R is 110 ohms. So that gives us the voltage. Okay, so you can calculate that will be 4 point or 47.3 volts in that case. Okay, and then now n is equal to 1, so then delta phi over delta t is basically equal to minus of that. Okay. So, but we are looking oh, sorry about that. We are not looking for the change of the magnetic flux, but we are looking for the change of the magnetic field. Okay, so magnetic field, changing of magnetic field, the field instead of flux. So then we are not looking for that, but we are looking for so we have this guy. Now we can maybe just rewrite the equation here. So this epsilon is equal to minus of delta phi, which is B times A cosine theta is 1 over delta t. So this will be, area is not changing, so there will be change of that over dt delta t, a minus there, and then times area. So we are actually looking for this whole thing here, a change of the magnetic field. Okay, so then this delta B over delta T is actually equals to minus of epsilon over A. Okay, so this is then minus of 47.3 volts divided by 7.2 times 10 to the minus 2 square. Okay, and that will be equal to minus of 6.6 times 10 to the second Tesla per second. Okay, now we are just looking for the rate of this changing, so that means we are looking for just the magnitude. Okay, so just the magnitude will be just that. You can ignore the negative sign. All right, so that's on that one. Go back to the slide. So the negative sign in the equation of the Faraday's law actually that gives you, that is actually the Lenz's law, which says that the induced current always flows in the direction that opposes the change that causes it. Okay, so that's the minus sign, which this is opposes it. Okay, so therefore, if the magnetic field is increasing, the magnetic field created by the induced current will be in the opposite direction. And if it's decreasing, it will be in the same direction. So for example, if you have a coil here, you are now moving this bar magnet close to the coil. So then the magnetic field in the coil is actually increasing. Now, the coil does not like that. So it will actually create a magnetic field in the opposite direction of that guy. So that means you can use your right hand rule here to determine what's your current in this induced in this coil. So B field will be in the opposite direction. So that means it should be in that direction. Okay. So you can put your four fingers in that direction, and then your thumb will be pointing in the current direction. So at the top of the coil, it will be going in this direction. At the bottom of the coil will be going in the opposite direction. Now, on the other way around, if we are pulling the bar magnetic field away from this coil, so now magnetic field inside the coil or the magnetic flux inside the coil is decreasing. So the coil does not like that. So you'll have an induced current that produces a magnetic field that to make up the loss in certain ways. Okay, so in that case, the B field should be in the direction of this bar magnetic field's field. So then in this direction. So according to your right hand rule, again, thumb in the direction of current, four fingers coil in the direction of B field. Okay, so then you'll get this current direction. All right. And similarly, a few more demonstration over here. So this is pretty much similar to what we had previously, but if you are going, in this case, you may have multiple coils, okay, multiple turns of coils, but it will be the same scenario, okay, for these two. And then if you flip, it will be the other way around, okay, so we'll just quickly just kind of skip that one. Lastly, we will take a look at if we have a piece of metal instead of wires in the magnetic field. Okay, so if you have a piece of conductor instead. So if you have a piece of conductor in the magnetic field, if there's motion of magnetic field relative to the conductor, then there will be actually induced current, which is called eddy current in the conductor. Okay, so if you have a sheet of metal, you make it move in the magnetic field through the magnetic field, then there's eddy current there. So again, this is similar to this is kind of induction. So the metal does not like that, so you'll have an induced eddy current that's opposed to motion. So if this piece of sheet is moving down, the magnetic field on the eddy current will be going in the upward direction. Okay, to actually oppose that change. So this has in a lot of applications. For example, in the car's brake system, so there's coils over here that you apply current to produce magnetic field, and when you do that, you create eddy currents in the metal sheet here in the brake. So then you'll slow down the motion of the brake. Okay. So that's your car's brake system. And if you have a piece of sheet here going through this magnetic field over here, so the presence of magnetic field will damp the motion of the sheet and then will make it stop moving rather quickly. You can also get rid of that damping factor by making cutting a lot of openings in the sheet. So then the eddy currents that will be inside each small stripes will actually cancel out. So let's see that in the next a couple of slides here. So first on the damping factor here. So if you are moving in this way, eddy current will be that way, magnetic force will be opposed to the motion. And then if you are going in this other direction, so then the force and motion again will be opposed to each other. You can use your right hand rule to determine the direction of the force. Okay. And then to remove the damping factor, so if you have openings there, so eddy currents here and here, neighboring ones will cancel out each other. So in this case, you can see, so current going in this direction, in that direction will cancel out. The forces will be in opposite direction. They kind of cancel out. Okay, so that's how you get rid of damping factor there. Application in metal sortings. So if you have trash, recycling trash that which have metals, so you'll have a magnetic field somewhere here. So then metals will be accumulated over there because of the damping factor. When it slides down, metals will be damped and then stay there. And also metal detectors in the battlefield. So magnets here. And if there's metals down here, when you have the magnets motion up above it, will actually detect the metals down there. So then you get signals there to know there's a metal down there. Okay. All right, so kind of summarize. So we talked about inductions, and then we talked about Faraday's laws that you can use to calculate the induced EMF, and then we also look at example where you can actually calculate eddy current or the current in the coil, induced current in the coil by using this induced EMF over a resistance. Okay, and the minus sign in the Faraday's law is according to Lenz's law because the coil does not like the change that any motion posed on the magnetic flux through the coil. And then we talk about eddy current and the applications of eddy current. Okay, we'll stop here for today and then we'll come back another time. Okay, see you guys next time.